All right, we need to talk for a few minutes just about satellites. Okay? And I know you've all heard of satellites, but I wonder if you really know what they are in terms of physics. If I were to ask you for a definition of satellites, you'd give me all kinds of different things, but really the definition of a satellite is simply any smaller body orbiting a larger one. Any smaller body revolving around or orbiting a larger one. Okay? So, yeah, we have television satellites and GPS satellites and all of those orbiting the Earth. But if it's any smaller body orbiting a larger one, then it means that the planets are satellites for the sun. And the moon is a satellite of the Earth. So really we break satellites down into two categories: natural ones, which are the planets around the sun, the moons around the planets, and artificial satellites. And these would be our television satellites, our weather satellites, our GPS satellites, our spy or defense satellites, our communication ones for our phones and things. Okay, so but they all obey the same physics. Okay, and who was the first person that figured out that we could do artificial satellites? It's our good friend, good buddy, Isaac Newton. He was pretty handy to have around. And he figured this out back in the 1600s. He just couldn't do it because we didn't have the technology. But what he realized was that really all a satellite is a horizontal projectile. So he imagined that if you could be high enough above the surface of the Earth where there'd be no air resistance, so you have to be high enough up where there'd be no atmosphere, dense atmosphere where there would be air molecules. So if you're high enough up so you wouldn't encounter any air resistance, and you gave this object a big enough VIX, then as it traveled outward and got pulled down towards the Earth would fall away underneath of it because the Earth is round. And so what would end up happening would be that as gravity pulled it down, it would fall around, it would continually fall around the Earth and never get any closer, right? Because if it was given a big enough velocity, it would curve around the edge of the Earth instead of just falling in. Okay, so that's really all a satellite is. It's an object that we have to place high enough above the Earth where there's going to be no air resistance, and then we need to give it a big enough VIX that then the pull on the Earth will exactly match its centripetal motion, right? So that FG becomes FC, and it falls around the Earth, constantly orbiting the Earth and never getting any closer. A satellite is simply an object in motion, then it stays in motion. It doesn't run on gas. It runs on the principle that FG is supplying FC. Okay, so if let's say we put a satellite up at a height of 50,000 meters. Okay, and so we could get its radius of orbit then, would just be the radius of the Earth plus the 50,000. Radius of the Earth is 6.38 times 10 to the 6th, and then we would have to add this 50,000 meters on. And when we did this, we could find the speed with which it was going, right? So if we know that FC equals FG, then which is equal to mv squared over r, then g m of the Earth, m of the satellite over r squared is equal to m of the satellite v squared over r. So our mass of the satellite cancels. When r cancels, we get back our v squared equation that we had derived there the other day. So g mass of the Earth over r. So v squared is equal to 6.673 to the negative 11 Newton meters squared per kilogram squared. mass of the Earth, 5.98 to the 24th kilograms. And then the R, 50 to add it to that should be 6.43. Yeah, times 10 to the 6th meters. And you'll get your V squared out and then take the square root. I didn't do this, but I guess I should. 6.673 to the 11th times 5.98 to the 24th. Divided by 6.43 to the 6th. Take the square root. I think I screwed up. And I put in my exponent. Shoot, just a second. All right, let me try it again. I don't have the answer there either. I thought I had done it somewhere else. 6.673 to the 11th times 5.98 to the 24th divided by 6.43 to the 6th square root. Oh, I didn't screw up after all that. 7,877.813 meters per second. And we could, that's a pretty good speed. We could use this to find out how long does it take it to go around, because we know V equals 2 pi r over t. So t would equal 2 pi r over this speed. So 2 pi times the 6.43 times 10 to the 6th meters divided by this 7,877.813 meters per second. And you could find how long would it take this satellite to go around the Earth once, times 2 times 6.43 to the 6th, right? And you get 5,128.4388 seconds. Now, I don't know about you, but that doesn't mean a lot in my life. So if I divide it by 60, 5,128.43. If I divide it by 60, I find out that's 85 minutes. So this satellite would go around the Earth once in 85 minutes. That's pretty quick. That would be great for a defense satellite. It would not be so great if it was our television satellite, because we'd be in the middle of a movie and the satellite would be on the other side of the Earth and we'd lose the signal. So some satellites we actually want to be this low so they can go around quickly. And I don't think I said it earlier, but most satellites are put above the equator. Okay, so we'd want them to go with some satellites, like defense satellites, to go around this quickly, but others we'd want to stay more above the same spot on the Earth. And that more above the same spot on the Earth, if you have the Earth and you want a satellite to stay above the same spot here as it orbits, it means it needs to go around at exactly the same time as the Earth spins. It means that the period of the satellite must be equal to 24 hours, because that's how long it takes the Earth to spin. When there is a satellite going around the Earth that's in sync with the Earth above the same spot, whose period is 24 hours, it's called a geosynchronous satellite. Geo means Earth. Synchronous means in sync with the Earth. So whenever you encounter a question that says it's a geosynchronous satellite, you're really being told two things. One, that the period of the Earth is 24 hours, and two, that the central body is the Earth, and you know its mass. So we could then, like a few minutes ago, we figured out how long would it take a satellite that was put 50,000 meters above the Earth to go around. So now we could find out what must the height of a satellite whose period is 24 hours, how high above the Earth does it need to be? Okay, and so we could do that by finding its radius of orbit. So I would do r cubed over t squared is equal to g mass of the Earth over 4 pi squared, and I'd solve for the r. And we're going to run out of time, but we're going to do it anyway. So bring your t squared up.